Our speaker tonight was formerly a tech lead at Google and is currently the tech lead at Cloudera, as well as the architect of Impala. Please welcome Marcel Kornacker.
Look down at the screen. So I'll be talking about how to build analytic applications for big data style workloads using Impala, but not just Impala, but the Hadoop stack in general. So this is going to be about something that is using an all open source stack for, is that recommended? Yeah. Okay. All right. For analytic applications. And to start out with a motivating example, here's a workload, a benchmark we ran a little while ago that compares a closed source commercial competitor against Impala on a subset of the TCDS workload. And this shows latencies, so response times, and Impala is the blue one, and obviously lower is better. So what you can see here is that Impala is already beating, on this particular workload, this particular commercial competitor, the name of which I'm not allowed to divulge because of licensing restrictions, obviously. But you can see that with the right setup, you can already get performance that is on par, in this case exceeding that of commercial systems. So this is set up running on HDFS with Parquet, and that is basically the topic of what I'll be talking about today. Just a little background. So Hadoop, so first of all, who here uses Hadoop? A few people, not the overwhelming majority, but a few people. So just to give some background, Hadoop has usually been utilized for mostly batch processing. So a lot of things run with a lot of latency and therefore are geared more towards batch, where the individual query latency doesn't really matter all that much. So now the question is, how do you utilize this system for something that is important for business intelligence style applications, so enterprise data warehouses that have a different set of requirements. Namely, you run queries interactively, and there are a large number of users that want to run queries, probably using a BI tool against a shared cluster setup. So I'll be going through the individual components that allow you to make that happen in Hadoop, namely that is HDFS, and I'll be talking about the specific performance-related aspects of HDFS. Then also Parquet, for those of you who don't know Parquet, it is a columnar format, and then some background on that, and also some showing some graphs that demonstrate the performance. And then the bulk of the talk is going to be about Impala and the features and also architectural characteristics. And what I'm trying to demonstrate is that you can already have a lot of the functionality and also a lot of the implementation techniques that are known from commercial proprietary systems available in the Hadoop stack. So I'll start out with HDFS. HDFS is the Hadoop file system, and it's a standard component of any, most, if not all, Hadoop installations. And what a lot of people don't know is that you can actually get very good performance from HDFS as it is today. In particular, data scans can be done with basically utilizing the performance resources. There are also some roadmap items that are interesting for analytic workloads. One of them is something that would allow you to do co-partition tables, and then also something that is good for iterative workloads, which would be like a 10-file system type functionality. Talking about data transfers. So one thing that has been available in HDFS for a while now is the ability to do short-circuit reads. So what that means is you get to bypass the data node. So in HDFS, you have a data node that is basically the master of the local storage on a particular node. And that is what you interact with when a client is requesting a data transfer, reading data from HDFS. Now, if your data happens to be local to the node on which you're making the request, you can, through the HDFS library, basically bypass the data node protocol and talk directly to the underlying operating system, which then basically gives you the data at full hardware bandwidth. So we routinely measure speeds in excess of 100 megabytes per second per disk on your server. So that is basically as fast as the hardware allows. If the data is not sitting on disk, but you want it to be memory resident, there's also a new feature in HDFS as of, it was available in CDH 5.0, which is called HDLS Caching. Basically, you would designate a file or a set of files contained in a directory as being cached. And what that means is that the name node of your HDFS cluster decides that one of the data nodes should hold this data in memory. And the name node would then know which one it is, so the client could find out at which node it is being held in memory. And then when you're making local requests on that client, you do not need to utilize the data node protocol or anything like this. You can map that memory through basically memory mapping operations, mmap and mlock, into your address space, and then read the data as if it were resident in your address space in read-only mode, of course, right? So that means you would get full memory bus bandwidth in order to access that data. So on some benchmarks we ran, comparing that to getting data out of the operating system buffer cache, you end up with something like 3 times the available throughput. Some things that are on the HDFS roadmap that are not quite ready yet. One is a feature called affinity groups. Affinity groups is a physical structuring mechanism for data, which allows you to co-locate the blocks of different files on the same server. So this would then give you the ability to decide to co-partition 2 tables. Let's say you do hash partitioning of a table, and you have 2 tables that are frequently joined. You could then co-partition those tables and turn what are normally distributed joins into local joins. Another thing that is being discussed in the HDFS community is the ability to have a temp file system like structure, so that if you do iterative workloads that need to write data and then read that in a follow-on step and do that repeatedly, you could simply write the data directly into memory. It would never have to hit disk. It would never get to need to get replicated, etc. So you would get a speed up for iterative workloads. This ends the very brief HDFS section of the talk. Are there any questions? On to Parquet. So Parquet is, as was already announced here, a columnar file format. Parquet was designed, was a co-design between Twitter and Cloudera, and we found out that we were both interested in the same thing and working on the same thing. So this was about probably 2 years ago. The goal here was to create a state-of-the-art file format that is as performant as you would get from proprietary systems. So most analytic database systems, if not all today, support columnar storage. And all of those file formats are, of course, proprietary. So the goal here was to create something that is open source and widely available so that it can be shared between frameworks. So Parquet is supported not just by Impala, but also you can read Parquet data through Hive, Pig, of course, MapReduce, Cascading, and I don't know what else. And as a result of that, Parquet was, like I said, developed by Twitter initially and Cloudera, but is now used in production by Twitter, Criteo, that's an advertising company in Paris, and also LinkedIn, as far as I know, and I don't know who else is interested in it, but there are a number of companies that now use that as their primary storage format. Parquet differentiates itself from other columnar formats by giving you an optimized format for nested data. So that means it uses in particular the Dremels column.io format, and which has a very compact representation of a nesting structure in your data. So if you use otherwise use Thrift, Avro, or XML, or JSON, it would be possible to convert that into Parquet and then have very fast scans and processing of the data. Parquet supports an extensible set of column encodings. So in the current version, which is 1.02, you already have run length and dictionary encodings, which give you very high compression and also very good decode speed. And you will see delta and optimized string encodings in the 2.0 version as well. So in particular, delta string encodings and then utilizing that for dictionaries. So you will see even higher compression factors and faster decode speeds. What you will also see in 2.0 is embedded statistics. So Parquet is internally, the data for one particular column is internally broken up into pages. Now these pages can have small amounts of statistical information such as min and max, which allows you to do very fast scans that can skip data that you know doesn't match your search criteria. Parquet 2.0 is also, we're discussing right now also the availability of an indexing, index pages and an indexing option, so that if you have sorted data files, you would be able to build out an index, a compact index inside of it, basically an ISAM structure, and therefore do single row lookups into the file. Here are some performance results. This shows encoding compression efficiency relative to a number of formats. So what we did here was we took the TBCH line item table from a 1 terabyte scale factor data set and then encoded it in various formats. On the very left-hand side, you see text. So this is obviously the original 750 gigabytes worth of data. And then moving on to the right, on the very right, you see sequence file with gzip compression. And right next to it, you see Parquet with snappy compression. And as you can see, Parquet and sequence file with gzip are roughly on par. So despite the fact that snappy is doesn't give you the same compression efficiency as gzip, but it is much lower CPU overhead on the decompression side, so it's advantageous for running queries. But with Parquet, because of dictionary encoding, you still get the same compression efficiency that you would otherwise get with, in essence, gzip over raw text data. And you also see a number of other things here. To the left of Parquet, you see RC file, also with snappy compression. RC file was an older columnar file format for Hadoop that was, I think, developed by Facebook. And RC file in particular has some design flaws that make it less than ideal, both in terms of compression efficiency and also decode efficiency. And that basically motivated the development of Parquet. Here is an experiment that shows the scan efficiency. So what we did here was we ran a bunch of the TBCDS queries, again on the 1 terabyte scale factor data set, and again on in a number of compression and in a number of file formats. Blue is again text. Red here is sequence file with snappy. Then next to that you see RC file. The orange bar is RC file with snappy, and the green bar is Parquet with snappy. So what you see across all of these is that there's not a single case where Parquet encoded data performs worse than any of the other formats. So we didn't bother including Parquet with gzip or anything else with gzip here, because gzip, like I said, has such terrible runtime overhead that it is really only useful for archival data and shouldn't be used for actively queried data.
Wait, can you specify the test a little bit more? When you say scan, did you just scan and grab that all the entire projection, or just one column?
Oh no, in this case we're actually running these queries of the TBCDS workload. So TBCDS specifies a data set, a schema, and a workload of about 100 queries, and we ran a subset of these for the sake of the comparison. So this is end-to-end query execution time, not just a scan. All right. This ends the Parquet section of the evening. If there are any questions, otherwise I'll move on to Impala. As the header here shows, Impala is meant to be a modern open source SQL engine. It was designed from the ground up. Work started around 3.5 years ago. And it was designed for performance. So to that end, it is written in C++, where performance matters. And then parts of it are written in Java, such as the planning, parsing, analysis, and planning section of query processing. It basically
are parts of it also in Python? There are parts of it in Python also, I think.
Well, not of the execution engine itself. There is a Python interface called Impala. And yes, so that is obviously then in Python. Impala basically implements traditional techniques that are known from MPP query engines. So traditional techniques that are used for basically data distribution and parallelism are also employed here in Impala. However, Impala was designed from the ground up for utilization in a Hadoop environment. So Impala is not a full database, it is the query engine part of a database. So it doesn't have its own storage manager, but instead it relies on the storage managers that you find in a Hadoop environment. In particular, there's HDFS and there's also HBase. Impala also utilizes other components such as Metastore. Metastore is a metadata repository that comes as part of the Hive query engine and is also used by other components, for instance, as part of HCatalog, to store metadata, to be a global metadata repository for a Hadoop cluster. There's another component called Yarn, which is a resource manager, a global cluster-wide resource manager, and I'll talk more about how Impala integrates with that. But this is another component that Impala utilizes instead of creating its own system. Impala was designed to run well in traditional BI tool environments, meaning that it speaks ODBC and JDBC, it uses Kerberos and LDAP for authentication, and it also supports ANSI SQL. So the goal here is basically that it is a plug-in replacement for existing analytic database systems. Like I said, development on Impala started sometime in 2011, and the first version came out in 2012, almost basically exactly 2 years ago. The initial 1.0 version came out last year in May, and we are almost ready to release the 2.0 version. So in a few days, presumably. What does Impala look like from a user's perspective? Like I said before, it's not a full database system, it is a query engine. So how do you make data available to be queried through Impala? You basically create tables that are virtual views over the physical data that is stored in HDFS or HBase. So as part of your create table statement, if it were HDFS resident data, you would then also specify a path into, for instance, to an HDFS directory that then stores the data. Like I said, you connect to it via ODBC and JDBC, and you then run standard SQL. Impala, in essence, supports ANSI SQL 92 with some extensions from the 2003 standard for analytic window functions. It also has correlated subqueries, and you can write UDFs, user-defined functions, and user-defined aggregate functions in both C++ and Java. And we are thinking about adding UDFs and UDAs for Python. Are there any Python users in the audience?
Yeah.
One, a few, okay, some more hands. All right. Would you like to have UDFs and UDAs in Python?
Yes. Yeah, I think it's actually, I've heard about the Impala, that they can run Python queries in, run Python UDFs in Impala. That sounds like a really good
addition. Okay,
good
so
addition.
We'll keep that in mind.
So you'd have a Python runtime in the Impala environment that would be able to load in things like sci-fi.
Presumably, the specifics of that we're still trying to figure out, but that's kind of the goal, that you enable machine learning type workloads that utilize these libraries. Yes. Impala supports a standard set of data types, so basically everything you're used to, aside from the only things that are not supported right now are date, time, and time. It does support timestamp, and also as of version 1.4, it supports decimal. In particular, they are mapped onto machine data types, so 4, 8, and 16-byte integers. So the computation in decimal in fixed point arithmetic is actually as fast as doing native floating point arithmetic. Some operational aspects. I mentioned HDFS caching as a feature in HDFS before. You can actually utilize that directly in Impala through Impala DDL. So in your create table statement, you can actually say you want a particular table cached in a particular pool. So HDFS caching then utilizes the concept of a pool. The memory needs to come from somewhere and needs to be counted in some way. So those are then, pools are then used to set up where the memory, what the memory then gets accounted to. And here you can have, like I said, create a table statement where you indicate that you want the table cached, and you can also do that for individual partitions of your table. Let's say you have a partition for every day of the year, maybe you only want the last week or the last month cached. That is all possible to do through Impala. And of course you can also uncache these settings. A little bit about resource management. There are two ways of doing resource management in Impala, and you can actually combine them. One is called admission control, and that is basically the preferred way of doing workload management in a distributed environment where you have a lot of concurrent activity. So what you do is you set up resource pools that where you indicate the number of for each pool, the number of concurrently executing queries, as well as the maximum amount of memory that you want queries to use that run inside of that pool. These configurations can be done through Cloudera Manager, by the way. And admission control then runs on every node in the cluster. So Impala is a daemon-based architecture that runs on every node in the cluster, and each and every one of these nodes would then enforce basically the admission control, the configured resource limits. This does not require Yarn and the other component, the complementary component to Yarn called Llama. And this does work in CH4 and 5. So if you are more interested in Yarn, that would only work in CH5. As I mentioned before, you can, for each pool, you can specify the maximum number of concurrent queries, the memory, and also maximum queue size. So this is a global queue size. And what happens is that when a query runs, or when a user submits a query, that query is then assigned to a pool based on the username or the authentication credentials. And based on that pool, the query either is run right away if the pool itself is below all the configured limits, or the query gets queued if it violates one of the limits, or if the global queue length is exceeded, then the query is rejected. So this is one way of doing it, and there's also another way of doing it which utilizes a component called Yarn, which is a standard Hadoop component that was introduced to do basically global resource management. So one thing in Yarn in particular is the availability of what's called the resource manager, which is a central repository of resources and resource reservations. So there's a central component here in your system, and Impala can do resource reservation via Yarn for individual queries. So when a query comes in, it then gets translated into a number of resource requests that are then eventually submitted to the Yarn resource manager. However, that sounds good because that means you do not have to partition your cluster in order to accommodate multiple frameworks, because every framework that would support Yarn would go through the same central resource manager, so you would have complete resource sharing. However, there is an overhead associated with that because Yarn was really designed for batch environments. So if you use Yarn, you will see extra latency and lower throughput in your system. So these are clearly two different things that cater to two different workloads. You would use admission control if you need low latency and high throughput, and you run mostly Impala queries, or somehow resource partitioning is feasible. You are able to set it up so that if you run MapReduce side by side with Impala, you can set it up in Linux containers, and you're okay with that. If that doesn't work, there's Yarn/Llama, and I'll talk more about the Llama component later. That would then allow you to run mixed workloads, and where you wouldn't need resource partitioning. However, because there is the central resource manager, you are hit with this extra latency that's basically a round trip to this resource manager. Some new features that you will see in Impala 2.0. I already mentioned that Impala supports analytic window functions, so this is what you will see. Here's an example, standard stuff with partition by, order by clause, And you can also specify windows. This also includes the ranking functions, so rank, dense rank, row number, lead lag, etc. And you can specify explicit rows for those as well. Impala 2.0 will also support subqueries, correlated or uncorrelated in the where clause. So previously it only did that as inline views. Now you can also use subqueries elsewhere in the query. And another limitation was lifted. Impala previously used to execute joins and aggregation strictly against in-memory data structures. That has now been redesigned. So Impala can spill data to disk, intermediate results to disk, if that is required of the query. This is, of course, still done with performance in mind. In particular, it does not spill data that would still fit in memory. A little bit about roadmap. One of the most heavily requested features is the support for nested data structures. So in particular, data that shows up in Parquet or Avro or JSON or XML. Right now, if it has a nesting structure, you cannot query it, but that will also be lifted in one of the upcoming versions. So we will have then native support for that. That means you do not need to flatten your data as it comes in. And also it will be natively supported in SQL. So we will have SQL extensions that make the nesting structure accessible in a SQL-friendly way. Another thing that is often requested is support for S3-backed data. So if you're using Amazon, you might be storing some data in S3 and you might want to query it. And instead of having to load that onto a local disk, even if you run within AWS, we will have an option that lets you simply run against S3-backed tables. You'll also see additional data types. I already mentioned that the only standard SQL data types that are missing are date, time, and datetime, and we plan on supporting those as well in the not too distant future. And then additional SQL functionality. So Impala right now does not support rollup and grouping sets, so this is also going to be something that will be added in the future. This concludes the user overview. Are there any questions?
A quick question. You mentioned supporting nested data within SQL. These are your extensions or based on some?
That will probably be our extensions, yeah. We'll look at existing standards, but we feel like there isn't really a good standard out there. There isn't really that much support in traditional RDBMSs for nested data. So,
are you attempting to make it compatible with the way Hive, the way you query it in Hive, and?
So the question here, should I repeat the questions? I'll repeat the questions. The question is, would that be then compatible with Hive, the SQL? And the answer is not likely. Hive has some limitations in the way it expresses nesting structure, so I think we would do something that is a little more general and makes it easier to express queries naturally.
Okay.
You say nested. Are you including the hierarchy ID type that you find in MS SQL, or are you just talking about JSON type objects? In other words, will you have anything like a hierarchy?
I'm not sure exactly what, when you say MS, Microsoft SQL Server, presumably. I don't know exactly what that does, so I can't really answer that. So I would say, what you see in JSON or XML, that's the type of hierarchy. So in particular, having complex valued columns, so you can have arrays, structs, and maps.
Oh, this does recursive.
Exactly, yeah. Recursive
also, sorry, just out of curiosity, why were the date and time and datetime sort of afterthoughts? Or?
Well, I would call them afterthoughts.
Well, just curious, why?
They would deprioritize simply because it doesn't help if we have support for that in Impala directly, because all file formats are shared across a number of frameworks. So if Impala supports it in Parquet, but Hive or MapReduce doesn't, it doesn't really help our users. So we need to make sure that before we introduce a data type, it is supported across all frameworks and in all file formats. So that was simply a scheduling consideration.
You showed the create table statement. Is there the notion of creating an index statement, or does it not make sense?
So the question here was about indexing capabilities and whether that makes sense or not. And in a Hadoop environment, it actually does not really make sense. The reason is that in a traditional RDBMS, there is a single path of the data into the system. So that means that the system itself, the RDBMS, can monitor all data going in, and it can maintain indices. So you can create secondary indices, and it will maintain them automatically as you insert new data. That is not true in a Hadoop environment. So for instance, in Impala, you specify a table as by pointing basically to an HDFS directory. If you then copy new files into that directory, they become part of the table. They become visible. But Impala doesn't know about it until it runs a query. So there's no way for Impala to maintain a secondary index automatically. So that's why this is a tricky proposition. Are there more? Yes.
Just to clarify myself, would it be fair to say that by Impala you're providing a view of the basic Hadoop data in a relational framework?
That is a.
Is this a fair statement?
That's a relatively fair statement. I mean, like I said, it's basically the query engine capability, the query engine component of an RDBMS that you're being
I understand. If that's the case, why did you pick a relational view instead of some other view which might be more convenient?
Well, I don't know if it's more convenient. SQL is extremely widely used. I would say that it's the most commonly used way of accessing structured data. So that seemed like the natural fit for this problem.
So if I have large tables and I'm sharding them, do you support that in Impala?
Yes. So you can partition tables, and that will basically physically separate the data into multiple directories. And then when you run queries and you have predicates on the partition columns, it will apply that and then only read data from the partitions at that point.
And if I'm encrypting some PII information within the tables, how do you work with that?
I'm not sure to answer that. There are some ways of doing, like I said, PII stuff and encryption, but this is currently sort of in development, I would say.
What do current people who are using it with BI tools, while it doesn't support date, what are they doing in the meantime?
Timestamp.
What was that?
Timestamp.
Yeah, exactly. So the question was, what do you do if you don't have date? Well, there's timestamp. You can also use strings. So there are a number of built-ins that understand dates formatted as strings.
I'm wondering about you said the grouping sets were not supported. Is that something like grouping, like because you have a lot of aggregate functions? So
yes.
How are those?
No. Yeah, sorry. So to clarify, no, Impala does support aggregation and grouping. Grouping sets are an extension of basically rollup and queue. So the OLAP functions are not part of Impala feature set right now.
Okay, I missed that thing.
So I have three questions. Like first question is like you said that you don't support date time, but we can put it in timestamp and we can convert it into date time, whatever format you want, right? And the second question is like even we don't have encryption support, but we support binary format. So I can encrypt it with any open source encryption DLL or anything, and then I can put it as binary and I can retrieve it and I can decrypt it, right?
Yeah, I mean, there are several ways of working with encryption that are actually built into HDFS, etc. So I think this is a wide-ranging topic. I'm not sure we have time.
Yeah, but it supports binary data, right?
It supports binary data, but it has to understand the format.
There's some tricky stuff with the way it does certain kinds of group buying. Is that something they're planning to improve some of the options for things you can group on? I've seen queries that'll die with codegen errors doing certain kinds of group buying.
Okay. So what was the question? I didn't follow.
In the upcoming releases,
yes.
Are there plans to improve some of the group buy functionality to add where there are some limits?
I'm not sure. I'm not aware of any limits that you're
non-equijoin.
Oh, okay. So this is unrelated to aggregation. You're saying non-equijoin. There's cross-join. There's also support for implicit cross-joins. Impala does not do merge joins right now, so doing non-equijoins very fast has some limitations.
Yeah.
that will be addressed in upcoming versions, not in 2.0 yet.
I'm sorry, Impala is just for querying, or is the full CRUD suite of operations?
So Impala does support an insert statement. However, that's a bulk insert. Actually, you can do single row insert into HBase. But into HDFS, it doesn't really, you can do it, but you end up with individual files per row, which is not really good, obviously. So you can't do single row update or delete, because that is a limitation of HDFS, right? The data sits in basically immutable files. This would be possible against HBase. We haven't implemented that yet. Right? HBase has some other limitations, isn't used all that widely, so you see some of it, basically. Like I said, bulk load is possible.
Can you go over the partitioning feature again? Because you mentioned that Impala would handle the partitioning physically on file, but then previous to that, you said, in regards to, for example, the indexing, that it's an HDFS notation issue. So how does Impala go about actually doing things like a partition? You pointed at like a directory with a bunch of files in it.
Right. So the question here was, how does Impala implement partitioning? Basically, each partition is a subdirectory in the main directory. And when data comes in, it's simply the data files are then placed in that particular subdirectory. So it's basically, like I said, a physical separation or logical separation of the data. And Impala is aware of all the subdirectories in which the data lives and can then decide to read data from one or the other.
So it maintains its own internal cache or check on the way things are?
No, it's actually reflected in the directory structure. So the partition keys are embedded in the path, in the directory names. And this actually shares the same directory structure with Hive. So tables that you create in Hive are visible in Impala and vice versa.
Can you compare and contrast with Impala with Hive? You mentioned that they work together quite a lot, but when would you want to use one versus the other?
So Hive uses MapReduce, Impala does not. I'll show you some actually performance comparisons in a little bit that contrast the user experience. Hive has more, for instance, Hive has some SQL features that Impala doesn't have yet. So if you relied on those SQL features, that's what you would want to use. Also, Hive has built-in intra-query fault tolerance. So if you have let's say, an ETL job that takes a day, then maybe you want, and you're running it in a very large cluster, maybe you want to run it in Hive. That's basically it. All right. Let me move on to the quick overview of the architecture, and then I'll present some performance results that we obtained recently. So if you're familiar with how distributed database systems work, this will be in essence the same. You have an Impala daemon co-located with every node in the cluster that contains data. And when a query comes in via ODBC or JDBC, there is a query planner that takes a query, turns it into a plan, and fragments the plan, and then identifies the nodes that have relevant data, and then sends out the plan fragments to the individual nodes. So here, the Impala daemon, the orange thing that contains the query executed as a component, will then run against the local data, perform local processing, scans, joins, pre-aggregation, etc. And then, while that's happening, exchange data among them. This is always point-to-point and process-to-process. So Impala does not materialize intermediate results into HDFS. So, for instance, unlike Hive. And that's basically how query processing works. So, talking about planning. Planning is also, again, here's what you're a great deal of familiarity with traditional RDBMS concepts. So Impala does cost-based join or optimization based on available statistics. It also does cost-based join distribution optimization, so it can decide between broadcast joins or repartition joins, again, based on available statistics. And after the initial single node planning process, which produces a tree of operators, it then goes and partitions that itself, breaks it down into plan fragments that are then assigned to individual nodes. So this fragmentation process, the purpose here is to maximize scan locality and minimize data movement, and then also maximize the amount of local processing you can do. So as part of that, it is able to parallelize all joins, aggregation, and all scans, obviously. One note about the execution engine. As I mentioned before, this was written from the ground up in C++. There's no MapReduce, and Impala was also designed to be able to take advantage of all available memory, so that aggregation results and the right-hand side of joins are executed as hash joins, and the right-hand side inputs of those joins are held in memory as much as possible. Only that part that doesn't fit will then end up being stored to disk. Impala also uses a novel technique called runtime code generation. It uses a tool called LLVM for that purpose. So what it does is basically each query engine is internally structured basically as a sequence of very large loops over batches of the data. And Impala manages, by using LLVM, to compile those large loops into machine code that is optimized for the query at hand. So it minimizes interpretive overhead, it doesn't have to look at the data types and branch on the data types. And it also avoids virtual function calls, which are extremely expensive and wreck your processor pipeline. Here's an example of what that speed up gives you. This was executed in a 10-node cluster, and these are basically 3 queries. The one on the left is a very simple select count star, again from the line item table, and the one on the right is the TPCH query one, which does a bunch of more complicated aggregations over that same line item table. And you can see here the latency with and without runtime code generation. The blue is without code generation. The orange one is with code generation. And you can see that depending on the complexity of the query itself, you get very dramatic speedups. A note about resource management. I brought up Yarn integration earlier. Yarn, the Hadoop centralized resource manager. And as I mentioned before, Yarn has a more batch-oriented view of how a cluster should be run that conflicts with how Impala wants to acquire resources for individual queries. So we created Llama as an intermediary between Yarn and the Impala daemons. So, and this is done on the one hand to make it more natural for Impala to talk to Yarn, but also to mitigate some of the design aspects that make it hard for Impala to integrate with Yarn in the first place. So one is the high resource acquisition latency that you naturally have with Yarn. And what Llama does is to cache resources in between requests so that you don't always have full round trips into the Yarn resource manager. One problem is also that resource requests are immutable. Once you made a request, you cannot augment it. And Llama deals with that by doing expansion requests. So basically a single query will result in a number of requests that are then held and released together at the end. And there's also the fact that in Yarn resource allocation itself, the granting of the resource requests is incremental. So you could get some memory on one node, but not on another. And of course, it doesn't help Impala because once a query starts up, it basically runs on all nodes that have relevant data. So it doesn't help you if you can run on one node, but then not on the other ones. So Llama deals with that by doing gang scheduling, in essence. I want to talk about some performance results that we got. This is a benchmark, again, based on TPCDS, a 15 terabyte scale factor data set run on a 20-node cluster. And this is a comparison of the latest publicly available Impala release right now, 1.4, and the most recent releases of a number of SQL and Hadoop solutions, such as Spark SQL, version 1.1, Presto is a system from Facebook, now available in version 0.74, and then the latest version of Hive, also called Stinger, or Hive 13 with TES. So TES is this runtime option that is supposed to mitigate a lot of the downsides of running, in essence, MapReduce jobs. And what we did here is these are single user results. And what we did is we took a subset of the TPCDS queries and then bucketed them by the amount of data they access. So the interactive bucket accesses the least amount of data, and the analytics bucket accesses basically the full data set. And what you see here are the execution times. The blue bar is Impala, and then from there on you see Spark SQL, Presto, and Hive on Tez. And as you can see, there's no single category where Impala is actually slower than any of the competitors. In particular, you can also then contrast that with how Hive works. So even Hive with Tez, i.e. with sidestepping MapReduce, still has a severe performance degradation. Single user is interesting. However, most BI environments really need multi-user operation, and so we also then decided to benchmark that. So what you see here are the queries in the interactive bucket. The bar on the left is the single user number, the latency, and the bar on the right is the same latency but now running 10 queries concurrently. So this is single user versus 10 users concurrently. And you can see that from Impala runtime, the latency doubles roughly, goes from 5 to 11 seconds. For all the other systems, it tends to go up quite a lot more. And in particular, then basically these are supposed to be interactive queries, right? And of course, something that takes 200 seconds to complete isn't really interactive anymore. Here's another view of that same system, same setup, same cluster, now measuring query throughput. And this kind of gives an indication of what size cluster you would need in order to satisfy a given set of users. And as you can see, comparing Impala to any of the other ones, you can see that they use they're much more runtime intensive and use a lot more compute resources in particular, which is why there's such a great degradation of query throughput. Some examples. So one of our customers is a global payments processor. Again, names I cannot divulge, but what they did is they do a fraud detection application, and they decided to replace their DB2 instance that relied on a storage area network with a Hadoop cluster running Impala. Ended up being a 52-node cluster, 300 terabytes in total, and they have a daily ingest of 2 terabytes. So, and then are planning on expanding their cluster. And that gave them a savings of 30 million annually because the storage area networks are extremely expensive. So it's not just the proprietary software licenses, but of course, basically hardware like this is also very expensive. So one major advantage of Hadoop environments is obviously commodity hardware.
So this implementation replaced what? Very briefly, what did this beat out? What was there formally in place?
There was a DB2 setup with the SAM. So I don't exactly know how many nodes it was. It was not 52, it was probably smaller, but similar disk capacity and overall capacity.
The performance testing you did, was it using the Parquet
Yes.
file format?
Yes, sorry. This was, all of these utilize the best file formats that are available for these systems. For Impala, that's Parquet. For Spark SQL, that was org file at the time. For Presto, that was RC file because they didn't have Parquet support or org file support. And then for Hive on Tez, it is org file.
Can you give like just an estimate of the impact of like not using Parquet versus using Parquet? Like how much
well, I mean,
query time?
In terms of using Parquet, instead of using Parquet, what else would you be using?
I don't know, just text or sequence file.
I mean, text would be, sequence file in essence is text.
Yeah.
It's a splittable
Right.
text. The degradation is, you can see it here. Where is it? There. So this is roughly the degradation that you're going to see. Right? The blue thing is uncompressed text. Parquet is down here.
Right.
So, you know, in some cases not much.
10.
Some cases factor 10. Yeah.
Okay.
It's pretty dramatic. Another use case that I can talk about, their reference customer, Media Math, they're actually in New York. A demand side platform, so they're an ad tech company. They do data aggregation based on the incoming data, and they had a very hard limit of, very hard SLA of 30 minutes that they managed to accomplish with Impala, where they started out with Hive and Pig that were at a 6-hour latency, so putting this in place, And keep in mind that they actually did not move to a columnar format. They're running this on text data because they felt they didn't want to deal with the extra processing step. So, but even with that, you managed to get a fairly large speed up. And there's also Allstate Insurance, another one of our customers. They are, in this case, this was interactive data exploration with a tool called Tableau. They just loaded a test case, sort of medium size, I would say, 2 terabytes in text, and did some performance comparisons as well. Some of the internal queries that ran in 2 minutes, then went down to 9 seconds, basically, when you ran the same stuff against Parquet data. And they also wrote a blog post.
Can you talk a little bit about these customers here? Using the previous customer, this customer seemed to be using text in a CSV or something like that. Can you talk about your tool's pipeline or process or recommended process for moving data from text source into Parquet format?
Sure. The question was, how do you best move data from text or whatever else into Parquet? You can, the way you would do that right now is you would create a table that has the text data, and then a mirrored table that has the Parquet data. And you can then simply issue a load command. So you insert into Parquet table, select star from text table, and it will do the conversion for you. We are, however, planning on making that process less manual and less sort of, obviously if you do that incrementally, you kind of have to stage it yourself, etc. So the goal here is that we would eventually have tables that have mixed formats. So you could have Parquet data live side by side with text data, and you would have a conversion process that runs in the background and it is automatic. So you add text data and then it would get converted into Parquet, and you would see the entire table and all of the data as it arrives.
So the pipeline of a standard current pipeline is some customers transactional systems are acquiring data continuously, and then they offload in some kind of batch frequency data into Hadoop, and then you can have an Impala executable run that says mirror into this Parquet file format, and that's how you're then archiving the data for future subsequent queries and analysis.
Possibly. So the question again was about what are the typical pipelines, etc. Oftentimes you do not see a traditional RDBMS transactional system as being the originator of the data. Oftentimes Hadoop is used as the sort of the landing platform for new data, simply because the storage is so inexpensive and it scales so well. So you would have data, let's say log collection, dump JSON files or text files directly into HDFS, and they are immediately visible to Impala. Just to summarize, I started out trying to explain that it is possible to do traditional analytic workloads with a fully open source Hadoop stack, and to that end we went through HDFS, Parquet, and Impala. So you get a lot of the functionality, however you still also get the advantages of the Hadoop environment, such as the flexibility, right? You have scale out. In essence, you add new nodes, and the system then expands across those new nodes, and also the cost effectiveness. Right? You're still operating with commodity hardware, and the storage cost and also the cost per core is very low compared to proprietary solutions. So just some prediction, what I think you're going to see in the future. On the roadmap, aside from functional enhancements, are also additional performance gains, and I think I can confidently say that at some point in the not too distant future, you will see Impala and possibly also other open source systems reach and exceed the performance that you now get from even the best performing commercial systems. The techniques are all well known, it's just a matter of implementing them in essence. You will see additional SQL capabilities. We talked about rollup, the OLAP functions, and let's say set, intersect, and minus. And you will also see much better workloads, much better resource management. So the ability to run mixed workloads in a cluster, MapReduce and Impala side by side, have different groups of users, and still do all that scheduling and maintain your low latency queries and high throughput.
So can you talk in the examples of the companies that you described? Can you talk about the time frames for migration from the traditional legacy platforms to
I think it's hard to generalize those. The question was about time frame for migration. I don't think there's a typical time frame. This entirely depends on the complexity of the setup, the how many people work on it, etc. Right? Typically, I would say customers start out with a smaller setup. They do a relatively limited, well-defined workload and data set, migrate that, use that as a verification of the platform, and then move on to bigger things.
Before we move on in QA, I just want to give a great big round of applause to Marcel Kornacker, Chief Architect. Any questions? Yes.
You mentioned metadata in the earlier part of your presentation. Could you briefly describe what kind of metadata you're talking about and which components actually use metadata?
Sure.
Query planner.
Yes, yes. So there are actually various forms of metadata in the system. Some of it is logical, so that is the tables themselves, the columns of the tables, the partitioning columns, etc. That is all stored in metastore, this Hive component. Then there's also physical metadata, such as the files that make up a particular table, the blocks of those files, as well as the block replicas of all of those blocks, and the disk volume, IDs, etc. So there's a lot of physical metadata that is obtained from the name nodes and the data nodes themselves, so from HDFS components. They are curated by a system, by a single node component of Impala called the catalog service, that is then distributed out to all of the Impala daemons. So all of the Impala daemons are peers, and each one can handle an incoming query, and it has the full metadata in order to do the planning and everything else. So you don't have there's no master node here, so you don't have the bottleneck.
Yes, over there.
For the different components that you would be putting together, it's like whether that be Parquet, one of the example companies decide to not use it because they don't want to deal with it. How complicated does the setup be in that if they change their minds later and they're looking at making a change, does that really dramatically change the setup they would have had to do with Impala, or?
Sorry, I'm not. Are you talking about a company that uses Impala and wants to move from another format into Parquet?
Yeah, so there's a bunch of different components, and if you're just getting started with it and figuring out what to use, and you decide you don't want to figure out one piece yet, and then you later want to transition, how complicated it is?
It's not very complicated. Like I said, you just create a mirrored table, and then you simply insert from one table into another. Okay.
Next question. I had it before. Yeah, dude.
So, I'm not sure if you've tried using Impala in AWS EMR, but do you have any tips, advice, things to watch out for using Impala in AWS EMR?
Not really. I mean, it's supported. I know that. Right now, because Impala doesn't support S3 storage, it's more, right, if you have your data in S3, you still have to basically pull it onto the local nodes, etc. So that's going to be...
I also know that Hive has a DynamoDB connector. I'm not sure.
Impala does not.
Yeah.
All right, we have time for just a couple more questions. Anybody?
You support S3 through S3FS or natively?
We don't support it yet. We are looking into adding that in the next version.
Time for one more? Yes.
Well, the Impala uses an HDFS store that includes structured and semi-structured data. Is this a fair statement?
I'm not quite sure. What is the particular question?
The question is, the Impala query engine is processing the data stored in HDFS, and that includes both structured and semi-structured data. That's stored as key value tags, right?
If you store this, so the question is, if you have semi or unstructured data in HDFS, what does Impala do with it? Well, you have to map it into a relational table, and so that's basically what you have. Usually when people refer to semi-structured data, they really mean complex structured data. So having things like arrays, structs, or maps inside your data. such as XML or JSON. And like I said, Impala will add support for that in one of the upcoming versions.
Okay, Marcel will be here for one-on-one questions for everybody to get a chance. Have a great big thank you, Marcel Kornacker.